Welcome to the sixth discussion that we shall have. In the fifth discussion, we had given a few examples of systems, both some of which were additive and some of which were not additive. Now, we look at those very examples and ask the question of homogeneity about those examples, as I asked you to do when we concluded the fifth session. I am assuming that you must have thought about it before we embark on this discussion. So, let us look at the first example that we took there. Y of t is x of t squared. Is this homogeneous or does this obey homogeneity? Let us ask. Multiply xt by a constant c. So, let us input c times xt to the system. Clearly, the output is going to be c xt the whole squared, which is c squared xt the whole squared. Now, although the output is also being multiplied by a constant, that constant is not the same as the constant by which the input is being multiplied. The output is multiplied by c squared, not c, and therefore the system is not homogeneous. I started with a negative example as before because it is important to emphasize the small errors that we often make. It might look like the output is also multiplied by a constant, but for homogeneity you need the output to be multiplied by the same constant. Now, let us look at the other examples that we had. We had y of t was x of t plus x of t minus 1 minus x of t minus 2. And we query what happens when c times xt is given to the system. C times xt would result in c times xt plus c times x of t minus 1 minus c times x of t minus 2, which is of course c times, you can take c common and make it c times x of t plus x of t minus 1 minus x of t minus 2, which is clearly c times yt. And therefore, the system is clearly homogeneous. Now, notice again that the fact that you had essentially a linear combination or a sum of inputs taken at different times gave you a homogeneous system. This is one sure shot way of creating a homogeneous system. In fact, this kind of a construct will be useful to us in many contexts, as we will slowly see when we proceed through the course. But for the moment, let me introduce one more new example here before we take the third example that we had in the previous discussion. So, let me take the example of the system y of t is t times x of t. What it means is the input is multiplied at every instant. When I say instant, I mean instant of the independent variable. So, if the independent variable is time, we are saying at every instant of time, the input is multiplied by the value of the independent variable. Let me make a remark on this system. What are we doing in this system? For example, if the independent variable were time, what are we doing? We are looking at the time and we are multiplying the input at that time by the value of the time. That means an input which comes at time t equal to 10 is multiplied by a number larger, namely 10, than an input which comes at t equal to 5. So, let us look at an input output relationship or an example of an input output relationship in this particular system. So, let us assume xt is the famed unit step that we had. We had introduced this unit step earlier. Now, we will formalize it and we'll give it a name too. So, unit step is equal to 1 for t greater than or equal to 0 and 0 for t less than 0. The unit step is often denoted by u of t. And if we give this input unit step to the system, what would the output be? The output would essentially be a ramp, t times ut, to be precise. So, now you see what I mean. whereas the input was constant from t equal to 0 onwards at the value 1, the output grows as time grows. And we will take this as an example to analyze the next property that we are going to see, but first let us complete the discussion on the current property, namely homogeneity. So, we ask, is this system homogeneous? Let us look at it. Well, give C times xt to the system, and what do you get? You get T times Cxt, and very clearly this is C times Txt, that is very easy to see, that is C times Yt, and therefore the system is clearly homogeneous. Now, here it is interesting, you have done something in the system which changes as a function of time, in the sense that what you are doing at time t equal to 5 is not the same as what you are doing at t equal to 10. In spite of that, the system is homogeneous, but it will reflect this discrepancy between what we do at different times will reflect in a new property, which we will see soon after this one. Before we go to that property, as I said, let us complete the last example that we had as far as additivity was concerned. Namely, consider the system y of t is xt plus 5 and ask, is this system homogeneous? Now, apply Cxt to the system and you can see the output is going to be Cxt plus 5. That is not the same thing as C times xt plus 5 in general, except for the trivial case C equal to 1. So, clearly the system is not homogeneous. In fact, therefore, it is neither additive nor homogeneous. However, I have placed both these examples on the same page here with an intent that they must be investigated for the next property that we are going to see. And let me introduce you to that property in this discussion and then take up the examples to analyze the property in the next discussion. The next property of a system that we are going to query is what is called shift invariance. So, let us first formally define shift invariance. Shift invariance, as the name suggests, asks what happens when you shift the input without making any other change. So, suppose you had xt being given to the system to produce yt as an output. What would happen when you gave x of t minus t0 to the system, same system of course? If the output is equal to y of t minus t0, and this holds for all x and all t0, that is very important again. It must hold for all x and for all t0. If this is true, then we say the system is shift invariant. Now, before we conclude this discussion and ask the question that we are going to do, before we take up the examples, let me give you an informal meaning of the term shift invariance. Let us say you have a laboratory apparatus and you have performed an experiment today on it, and you see the cycle of outputs that you got today in the apparatus. So you gave it some kind of sequence of inputs and you noted the trail of outputs today, and you came back to the laboratory tomorrow, set up the same apparatus and performed the same experiment. If you expect to see the same results tomorrow, and this should happen no matter which day or at which time you begin to conduct the experiment, then we say that apparatus is shift invariant. Except for a shift in time, there is no change in the output, provided you make only that change in the input, namely you have only shifted the input in time. You have not changed the input otherwise except a shift. Shift invariance is essentially a statement of whether systems behave as they do now at any point in time, and we shall see more of this in the next discussion. Meanwhile, think again about those examples that we have to answer whether they are shift invariant or not. Thank you.